I'll show you later for the YouTube one. But so last time we stopped at the telescoping series. So let me review it for you one more time. So what we learned in the past 2 days, we learned how to deal with the convergence of the series. So basically we have an, and then we take summation of an, start from n equal to 1 to infinity. For example, this is called a series. This is called series. We're trying to check if the series is convergent or the series is divergent. So there are so many ways to check the convergence of the series. The first way that we're gonna learn, we already learned one way how to do it, which is the geometric series. So the second way that we're gonna do is we're gonna learn how to do it with telescoping series. So for this one, what we're gonna do is we're trying to compute the form of Sn. Sn, this is the summation of the first n term. Once you compute your Sn here, if it is computable, you can compute Sn first, and then you take limit of Sn after where n go to infinity, and that will give you the limit of the series. So if this thing converge, if the limit of Sn convert and equal to S, we're gonna call that the sequence, the series is divergent, convergent, and if it is not a real number, we're gonna say it is divergent. So last time we went over two examples. So example 9 part A, we can see that once you have this series, so you can expand S1, S2, S3 and so on, and you have so many cancellation here, and at the end you get Sn here, and you take limit, you get 1/3. So the series convergent here. And the second example that we show you last time is we start from 1 over k times k plus 1 here. We split to the partial fraction decomposition, and then we solve for a and b, and then after that we compute Sn. So at the end we get 1 minus over 1 minus 1 over n plus 1, and then we take limit, you get 1. So the series is convergent. Let's do two more examples on telescoping series. All right, so I think everyone is ready now. So part C, how about the summation of logarithm of k plus 1 over k, where k start from 1 to infinity? How we start this problem? So first of all, here you can see that your a subscript k, this is actually logarithm of k plus 1 over k. However, by the property of logarithm, so the logarithm of a over b, this is the same thing with logarithm of a minus logarithm of b. This is the property of logarithm. If you don't know, this is going to be so handy for you to use later. So you can split this thing to log k plus 1 minus log k. Okay. The reason why I do this, because I want to see the negative side here, because once you see the negative side here, should be good later, because we're gonna trying to make some cancellations. So now you can compute Sn, right? Sn, it's gonna be like a1 plus a2 plus a3 and so on up to an. So basically you can start from the first term here, which is going to be logarithm of, you plug in n equal, k equal to 1, so it's gonna be log 2 minus log 1, and then plus a2 gonna be log 3 minus log 2, and then sorry, that's a2, so a3 it's gonna be log 4 minus log 3, and now you should see the pattern. Now it's gonna keep going, and then at the end you're gonna see logarithm of n plus 1, yeah, it's n plus 1, and then minus logarithm of n. So now it's come to the critical point. How do you cancel this thing? So for those of you who have no idea how to cancel, trying to think that you need to find a pair. So this is like the log 2 here gonna have a pair with negative log 2 here, so you cancel it, and log 3 here gonna cancel with negative log 3 here, And you can see the pattern gonna keep going. Log 4 here gonna cancel with something inside here. And well, with the last term, what do you have left? So basically the term before the last term gonna have log n, right? And then log n gonna cancel with this log n. So basically this term log n, it cancel out with something inside dot 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 here. Because the term before it, you should have log n minus log n minus 1. And this gonna cancel that. And then this one gonna cancel with the term before it. But you know, we just collapse it and then we just make it super short and then say dot 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 here. There are so many cancellation inside here. So what you have left at the end, you're gonna have only log 1 and log n plus 1. So at the end, you just show it to me that, hey, this is the final answer is negative log 1 plus log n plus 1. And now it's your turn to take limit. And if the limit exists, it is convergent. If the limit does not exist, it's just divergent. So we're gonna see limit Sn, n go to infinity. So this is going to be the same thing with limit n go to infinity minus log 1 plus log n plus 1. So when n go to infinity, this is constant. So it doesn't matter what it is, just constant. But when n go to infinity, n plus 1 go to infinity as well. And that log infinity is just infinity. Because the log here, remember the graph of log x? I would recommend for those of you who are not familiar with limit, trying to remember the graph of log x e to the x arctan x. So if you remember the graph, it's going to be a lot easier when you compute limit, because you can feel like, okay, log x go to infinity, it's going to go to infinity. Just going a little bit slower than the linear function, but it still go to infinity. So this should be plus infinity, but because this go to infinity, this is just constant, so we don't care. It doesn't matter when compared to infinity. So that means the series is divergent. Okay. All right. This is the technique called telescopic series. One question on exam 1, telescopic series. So the technique is trying to simplify until you see something minus something, and then it's gonna cancel. Compared to the previous example that we learned on Monday, you can see that we do the same thing. We do the partial fraction decomposition. So we see something minus something, and then it's gonna cancel. Okay. All right. I will let you jot down for a minute, and then we're gonna move to the next example. So for those of you who want to practice by yourself, you can start the next example by yourself. All right. Should be good for you now. So let's move to the next one then. Good. All right. So part D. This one is summation k start from 1 to infinity. 1 over square root k plus 1 minus 1 over square root k plus 3. Okay. This form super easy because you have ak already, and it's come in the form that something minus something. So this should be okay for you to do the telescoping series. So it's gonna be s subscript n. This is actually a1 again plus a2 plus a3 plus dot 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 up to ak, or an, sorry, a subscript n. And then now what you do is you trying to find the cancellation. So the first term gonna be 1 over square root 2 minus 1 over square root 4. Second term is 1 over square root 3 minus 1 over square root 5. Just plug in it. And then a3 gonna be plugged in, it's 1 over square root 4 minus 1 over square root 6, and so on. The last term that you have, it's gonna be 1 over square root n plus 1 plus 1 over square root n plus 3. If you feel like it is a little bit hard for you to see the cancellation, I would recommend you to expand more term. So you can just expand one more term before the last one, just to make sure that you see the pattern. So the the term before the last one, it means you plug in n minus 1. So the term before that gonna be root n and then 1 over square root n plus 2. This is the term before the last one. So if you are still not comfortable with the series here, you can expand more if you want to. For example, if you feel like you are a beginner and you don't see the cancellation, maybe you should do it one more term here. But it's up to you. I mean, some of you have more experience, so you see the pattern more easily. If I do it, maybe I'm gonna do one more term, 1 over square root 5 plus 1 over square minus, okay, minus 1 over square root 7. So I need to fix this one. This should be minus. Okay. So I think this is enough for me. So I expand 4 terms at the beginning, and at the end I expand 2 terms. So now I can see the pattern of cancellation now. So I can see that 1 over square root 4 here gonna cancel out with this one, and 1 over square root 5 here gonna cancel with this one, and every time the back one gonna cancel with the front one for the next 2 term, right? This gonna cancel with that, and 1 over square root 6 gonna cancel with something inside here, as well as 1 over square root 7. So everything here gonna cancel, but it's cancel with something inside here which you don't see it. And then what do you have at the end here? So you should 1 over square root n here should cancel with the term inside here, right? And 1 over square root n plus 1 should cancel with something inside here, because you're gonna have it like inside here anyway. Does it make sense? Yes. And then at the end you're gonna only have 4 terms left, which is 1 over square root 2 plus 1 over square root 3 minus 1 over square root n plus 2, and then minus 1 over square root n plus 3, which means this is your Sn, and then you take limit of the Sn. It's gonna be limit of 1 over square root 2, 1 over square root 3, and then minus that one. Let me keep going. So the answer is gonna be just the number that we have here, 1 plus square root 2 plus 1 over square root 3. This is gonna go to 0, this is gonna go to 0, because the bottom is heavy as we talked before. So the answer is gonna be just that and that. So which means the series is convergent. For this one, we also know that the limit is going to be that number. So, and its limit or its summation is 1 over square root 2 plus 1 over square root 3. The good thing about geometric series and telescopic series is that you know the limit, because the limit, when you talk about the geometric series, the limit is the first term over 1 minus common ratio. When you talk about the telescopic series, this is going to be your limit, the summation that you get it from the calculation. Okay, for those of you who just show up, so I post the clip, the recording that I record here in my YouTube channel. But I don't post the link in my course view, because it's just way too much to just copy the link and paste all the time. But you can go to YouTube and go to my channel Monchai.K, and then you're gonna see the clip for CHPE like on that one. So I'm trying to post it there 2 days after class. One thing is that if you have ISE friend that you want to watch the clip, so make sure that the notation that we use is different than them, because we use K but they use N. So but basically the technique is the same. You just need to do the same thing telescopic series, because we use the book that use K, so we're gonna use K. Alright, so next one, this is a technique. So now you already learned 2 techniques, everyone, geometric series and another one is telescopic series. So let's do the next one. This is the easy one, is the divergence test. Integral test is the hard one. Usually students have a hard time with integral test because you also can check the convergence of the series by looking at the integral of the function. By the end of this section, you're gonna have 4 tools to check the convergence of the series, and we're gonna cut the exam one at the end of this slide. So at the end of this section, so that is all the content that you're gonna have for the exam on February something. Yeah, February 1st, I guess. Okay. Ready for the divergence test? So we're gonna learn 2 more tools for this section 8.4. This is called the divergence test and the integral test. So let's start from the divergence test here. So let me talk about the concept of the divergence test, and then we're gonna come back to this page. So everyone look at this picture. So this picture is the picture that when you have limit of a sub n go to 0. So what happened is the theory gonna say that when the series is convergent, so you're gonna have limit of Sn equal to S. When limit Sn equal to S, it means that, hey, it means that the summation go to one number. So when the summation go to one number, it means that the term on the tail should go to 0. Because if the summation go to one number, if the summation of all these things go to one number, it must be the case that the term at the tail should be 0. I mean this you cannot see it here because this is the Sn, but if you graph a sub n, it's gonna be 0. So by this I mean let's think this way. So when you have this summation, actually the theory is on this page. So when you have the summation of, I zoom into it. Yeah. So when you have summation of an is convergent, okay, if you have that one, it means that your limit S subscript n, this is a partial sum, equal to S where n go to infinity. If you take a look at the term a subscript n, so a subscript n, this is going to be the n term of this of the sequence an. So it's actually, if you want to find the an, it should be Sn minus Sn minus 1, right? Because Sn gonna form by a1 plus a2 dot 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 up to an, and Sn minus 1 gonna be a1 plus a2 dot 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 up to an minus 1. If you subtract them, subtract each other, so you're gonna get just an, and then you take limit on the left hand side, you take limit the right hand side, because the limit of Sn and limit of Sn minus 1, it's gonna go to the same thing because the series convergent, so it's gonna go to the same thing. You can say S or L or whatever, it's gonna just go to the same thing, and that it go to 0. So which means if you know that the series is convergent, it must be the case that the last term, like a subscript n on the infinity, the last term on the far term over there should be 0. Limit gonna go to 0. Why do we care about this thing? We care it a lot because, okay, we're gonna have the theorem say that if the series is convergent and then limit equal to 0, which is the same thing as if the limit is not equal to 0, it means the series is divergent. So let's think one more time. This is the logic. So if you know that summation of k go to 1 to this one is convergent, so you can conclude that the limit a subscript k gonna be 0 because the last term on the far side should be 0. But by the thing that you learn in in high school, or the thing that you learn, the basic logic, you learn before that, hey, when you learn logic, it's gonna be like you have the statement P and statement Q, and then you learn before that, hey, the truth value could be true to false to, you've seen it before, right? And false. This is the the truth table for the logic thing. If you have the statement P imply Q, so when you learn in high school, it said it's gonna be true false to here. This is going to be the same thing with not Q imply not P, because they are the same thing. So if you try not Q imply not P, it's gonna give you true false to as well. So in mathematics, if you have statement P imply Q, it is going to be the same as not Q imply not P, because they are the same. In the truth table, they give you the same value here, which means if you swap this thing, the statement gonna be limit of AK is not equal to 0. If you have that one, you can conclude immediately that summation of AK, this is actually divergent. Does it make sense? And this is going to be the statement that we're going to use a lot. So when you have a series, if you can compute the limit and the limit is not equal to 0, bang, you're done. That means the series divergent. You're going to see it in the example pretty soon. But if you compute the limit and it is not equal to 0, it means the series divergent. Okay, I'll let you jot down here first. It is a good one, good logic here. That we can conclude the divergent easily by just taking limit. One thing that students fall in the trap most of the time is like when you get limit a sub k equal to 0, you cannot conclude that the series is divergent or convergent. You cannot conclude at all. It's follow here, but yeah. You cannot conclude that the series is divergent or convergent when the limit is equal to 0. It's gonna be the hard case. So, but when it is not equal to 0, yeah, you're good to go. So the series is divergent. So let's go to the example then. So you're done with this slide? Go. Let's go. This example, we just learned how to use the divergence test. The question said that check if the following series diverge, or state that the divergence test is inconclusive. So when limit of a subscript k not equal to 0, we're gonna say that the series is divergent. But when limit of a subscript k is equal to 0, we're gonna say that the divergence test is inconclusive. It means you cannot conclude anything from the divergence test. So you have two ways to answer. It depends on the limit. So for part A here, so you can see you have 1 over k plus 2023. So basically this is your an, or a subscript k, right? You take the limit of ak. Boop, and then you get limit of 1 over k plus 2023. K go to infinity. This gives you immediately 0, right? Because the bottom is heavy. So this means the divergence test is inconclusive. The divergence test is inconclusive. What should you do next after the divergence test is inconclusive? You're gonna learn so many truths next week. How to deal with the case that when the divergence test is inconclusive, you still have integral test, root test, ratio test that we're gonna learn next. But usually the divergence test, we're gonna check this one first, because in the case that the limit is not equal to 0, it's gonna be the easy job. You done because it's divergent. So let's take a look at part B here. This is done already for part A. For part B here, if you take limit of, well, this time this is your an, a subscript k, sorry, ak here. You compute limit of this one, k over square root 9k squared plus 1. Yeah, but this one you can see that the highest degree on the top is 1. The highest degree on the bottom is square, take square root. This is 1 as well. So you can do something like k over k on the top, and the bottom you're gonna have like square root 9k squared plus 1, right? You over k as well. So you just put k split, put k on the bottom and k at the top here. So it's just the same thing, right? You balance them, and then otherwise, and then the next one you're gonna do the next one you're gonna just say this is square root k square, and then put k square inside there. So it's gonna be limit of 1 over square root 9 plus 1 over k square. And then now when you take limit, it's go to 1/3. This is not equal to 0. The conclusion gonna be that the series here diverge. It is divergent by the divergence test. By the divergence test. Okay. Which means if you can compute the limit and the limit is not equal to 0, easy job, because it's gonna be divergent as well. This, you can use this one with the geometric series and telescopic series as well. If you feel like, Ajahn, I cannot find the common ratio, I want to take limit, and if you show me that the limit is not equal to 0, and then you say, oh, this series is divergent, fine, this is the same thing, so the answer gonna be divergent as well. Alright, so I'll let you jot down a little bit, and then we're gonna move to more example. Good one. Good one. The divergence test is easy. I like it because it's just, you just need to take the limit. Alright, next one. Alright, let's do the review here. A, B, or C here, they have multiple choice here. So the first part, if the series is convergent, what can you say about the 10 times the series? Convergent as well, right? Because you can pull out number 10 here. Converge. Right, because this is the same thing as 10 times summation A subscript K. So this is convergent as well. If the summation of AK diverge, summation of BK diverge, what can be said about the summation of A subscript K plus B sub K here? So actually here you can imagine that it's gonna be may converge or diverge, because if you think the first one, if you take AK to BK, this is divergent, right? And also if you take BK to BK, this is also divergent. And then if you add them up, it's gonna be summation of AK plus BK, it's gonna be the summation of 2K, which is, it's equal to 2 times summation of K. Actually this is divergent as well. But you could have the case that A sub K equal to K, B sub K equal to negative K, which means this is also divergent and divergent, but when you add them up, so they cancel, and then you get summation of 0, and you're gonna get 0, which is convergent. So this is the thing that you have to be careful. The divergent for the series and the divergent for the series, if you add them up, no conclusion. So you still are not sure what you're gonna get after you add the divergent and divergent. This is the subtle point for the series one. So we're gonna learn it later that divergent plus divergent, no conclusion. But convergent plus convergent, you get convergent, because it's pretty simple that convergent is go to one number, another convergent go to another one number, and then you add them up. It should be convergent as well. And the last one is convergent and divergent. Add them up together, you're gonna get divergent. Alright, so this is different from improper integral that you learned from the first week. Because when we learn improper integral, we're gonna just say if you see any small term that is divergent, it's gonna be divergent. Alright, so let's move to the next question. If the limit AK equal to 0, what can you say about summation AK? So the answer should be may converge or diverge, because the divergent test is not applicable. It means you still are not sure it's gonna be convergent or divergent. When limit is equal to 0, not sure. But when limit is not equal to 0, say the limit is equal to 1, for example, conclude เลย it's just divergent. Yeah, conclude เลยนะ Yep, convergent, divergent. Yes. Should I like I used to teach like I mean like my co-worker used to teach ISE student and get a complaint that from international student that he speak Thai a lot, so in class. So I'm try not to speak Thai because I am afraid that I'm gonna get complaint from you like yeah, but you know sometimes like it's not fair for you know like international students that because ISE they have so many Chinese students, so many you know yeah, not fair for them because sometimes like some teacher they just talk about the exam in Thai and then like international were like not okay, like yeah. Okay, so we have only two topic left for this handout. Once we finish, I'm gonna just summarize everything you learned from the first day up to today, and that's gonna be the content for the exam one. Okay, so let's move to the next one, harmonic series. So you may have a question that, Ajahn, what about 1/k? So 1/k looks pretty simple, but when you take limit, it is 0, right? So 1/k look pretty simple. It's like this should be the simple idea because summation of 1/k it's just 1 plus 1/2 plus 1/3 and so on. We should know the behavior of this thing easily because this is actually 1/k. But when you take the limit of 1/k where k go to infinity, it's go to 0, which means you cannot conclude anything from the divergent test because the divergent test you can conclude it only when the limit is not equal to 0. The divergent test cannot be applied here for series 1/k. So 1/k here we have the name harmonic series for that one. I think the name was adopted from physics class because physics class use 1/k a lot and then they give the name harmonic series to this one. So let's take a look again about the harmonic series. What if you use a calculator and then you compute S1, you get 1. S2 you add 1/2, you get 3/2. S3 you get 1/3, you get 11/6. And S4 you get 25/12. You still have a hard time to see what pattern it is. And can we conclude that it is convergent or divergent? This is a proof how to show that the harmonic series is convergent or divergent. Let's take a look at the proof pretty quick. This is the smart proof for you know for math student. They're gonna learn some trick like this in third year student, but I show you here. This is for the harmonic series. So the result is that the harmonic series 1/k. This case it is divergent. Why? Let's take a look. So if you expand it, it's gonna be like this. And then you can see that we say that this is L. Let assume that it is convergent to L. And then you're gonna have L here. So L here gonna be bigger than 1 plus 1/2 plus 1/4 here. Basically, I change 1/3 here to a quarter here because this one is bigger than that. And 1/5 here, 1/5 bigger than 1/6. So I'm gonna say okay, I change 1/5 to 1/6. 1/7 here I'm gonna change it to 1/8. And then because I use the number that is smaller here, smaller here, so this is gonna be the greater than 1. And then after that I group this thing up to be 1/2. I group this thing up to be 1/3. I group this thing up to be 1/4. I group this thing up to be 1/5. And then once you simplify the term, so on the right hand side you're gonna get 1/2 plus L, and L cannot be greater than 1/2 plus L, so you get a contradiction, which means the series here cannot be convergent, so it must be divergent. If you are interested in this thing, so this is how math people learn the proof or something, so they learn so many techniques how to prove you're gonna have the contradiction way to prove it or contrapositive way to prove it or something like that. But for you, just memorize that the series here is divergent, but the way to prove it, you have more than 50 ways to prove it, but this is the one way that you can do it. So 1/k is divergent. Summation 1/k is divergent because you can compare it with the term here, the odd term here, and then at the end you're going to get the contradiction if you assume that it is convergent. So the take home point for this slide is again the harmonic series divergent. Okay, next one. Now let's take a look. This one I already talked in the previous slide. So the property of the convergent series. So if you have the series that is convergent, if you multiply the constant, you can take the constant out and it is still convergent. If you have the convergent and convergent, you add them up, it's still convergent. But if you have divergent and divergent together, no conclusion, as I talked in the multiple choice question before. And also if you have the convergent, add them up with the divergent, it's gonna be divergent. I hope it matches with your instinct because the convergent and divergent, when it's grouped together, so the divergent is gonna be the one that win because the divergent go to infinity. It's gonna go to infinity or negative infinity anyway, so that means you're gonna have the divergent series after you sum convergent and divergent series. All right. Let's take a look at example. I guess this is the one that the mixed question. This is the last one before we go to the integral test, the last content for today. Okay, let's look at example 11. What if I have summation k equal to 1 to infinity e to the negative k plus 1/k? Convergent or divergent? Some of you are gonna say that, Achan, we learned so many things, but I cannot remember anything. Right? So when you see the series, the question gonna be the same thing. Is like you need to check convergent or divergent. So if you see something like this, first of all, you can split it. You can split it to that one. Because the summation, you can split it, right? 1/k, this is divergent, right? This diverge. Because this is the harmonic series. Right? 1/k always divergent because the harmonic series. What about e to the k? Convergent or divergent? This is actually the geometric series, right? Geometric series. R equal to what? What is the common ratio here? E to the negative 1 or 1/e. Does it make sense? Because summation e to the negative k, it is actually 1/e to the k, right? And this is actually 1/e to the k. Does it make sense? And that means you're gonna have actually you're gonna have the geometric series here, and the ratio, the common ratio is 1/e. So when you have 1/e as a common ratio, geometric series here, convergent or divergent? You compare to 1, right? If it is less than 1, convergent, bigger than 1, divergent. Does it make sense? Boop, and then you're gonna get here convergent. So convergent series, add them up with the divergent series. So at the end, the answer gonna be divergent. Yes, true. The series diverge. Okay, so which mean if you want to be expert in series, well, because this is only your second day to learn this thing, but you have to memorize how the series is gonna be convergent or divergent for the geometric series. for the telescopic series and for the harmonic series now, and for the divergence test. And the next one is for the integral test. You have about 10 tests to do it. Luckily that you have exam 1, so you're gonna have only 4 or 5 way for exam 1, and then after that you can throw away because it will not be on the midterm again. So part B here, 2 to the k plus 1 plus 3 to the k plus 1 over 4 to the k. How would you do it? Let's simplify. Look like it is a geometric series, right? Because you have 2, 3, and 4 here. Okay. It is 2 times 2 to the k, right? It is 3 times 3 to the k. And then you can split 4 to the k on both terms. Is that okay now? Because you split 4 like you... Yeah, and then now you just take the summation. So the first term is gonna be sum 2 to the k over 4 to the k, k from 1 to infinity. The second term gonna be sum 3 to the k over 4 to the k, k start from 1 to infinity. If you take the summation, so we need to find that one, right? Because we just take the sum now. And then here, geometric series, right? Here, also geometric series. Can you see it is geometric series? Because it's like the common ratio power to the k. So it's actually geometric series. So the first one r equal to 2 over 4 or 1/2. So the second one r equal to 3 over 4. Right? Which means both of them, they are both convergent. This is actually convergent. This is actually convergent because both of them, your common ratio r is smaller than 1. So it's actually convergent. And then now you can conclude now that the series is convergent. The given series is convergent. Easy one. However, the question asks you more that if you know that it is convergent, can you find it, evaluate if possible? So if you know how to find it, please find it. So of course, the first term that I highlight in yellow here, because it is geometric series, you can find it by, you give the limit is, so the first term over 1 minus common ratio, right? So the first term, you plug in k equal to 1. So you're gonna get 2 times 1/2, which is 1. And then 1 minus common ratio, which is 1/2 here. And then plus the second one is you plug in 1 over there. So you're gonna get 3 times 3 over 4, which is 9 over 4 on the first term. And then 1 minus the common ratio, which is 3 over 4. So again, for those of you who cannot follow me, the formula for the geometric series is the first term over 1 minus the common ratio. Okay, the ratio is 1/2 and 3 over 4. This is why I plug in r here. And then the first term here is 1 and 9 over 4 because I plug in k equal to 1. So I get 1. I plug in k equal to 1. I get 9 over 4. And then, well, for my class, you can stop it here. I'll give you full credit. You don't have to simplify it. So good for me because the rest of the work is like the calculator thing. Well, but for ISE student who watch this clip later, you need to evaluate it.
So normally the ISE have to calculate, right? It's mandatory for them to calculate.
Yeah, I mean actually you should be able to calculate it as well. It's like this is not that hard. Like it's just like this should be 2 plus like and then this is 1 over 4. Boop, this is 9. Yeah, am I right? 11. Yeah. But I mean, like in case that you feel like the calculation is your problem, you just leave it there. All right. This is the formula for geometric series นะครับ So now you can see how hard it is for the series. This is when you are, when you are sophomore friends or something like you are, the senior or junior year say that the calculus 2 is hard because of the series. It is true. It is hard because when you check the convergent and divergent, you have so many ways to do it. At least for now, you learn geometric series. You learn telescopic series, you learn divergent test, and you're going to learn integral test next, and then you have harmonic series. You already have 5 ways to do it, but next week we're going to learn another 4 to 5 ways. So you have about 10 ways to do it. And when it's come to the question, because you have so many tools, you don't know what to use. This is the hard one for this chapter. Okay. So the last one that we're going to learn, let me spend 15 minutes on this thing, and then we can get it done for today. So maybe at least I should do one example on integral test, and maybe part B, part C, we're gonna come back next week for more examples, and then that will be done for today. Okay, so let's take a look at integral test. This supposed to be the hardest one to use, so we try to avoid it. If it is not the worst case, we are not going to use the integral test. It is the hardest one to use because you have to integrate something. If you feel like Ajahn, I'm not good at integrate, try to avoid this one. Only people who feel like I'm more comfortable to integrate it, you can do it. Yeah. So the idea is that, let's take a look at the idea. If you want to check the convergence of the series, the idea is that, take a look at this one. Summation of n start from 1 to infinity, an here. If you take a picture of this thing, n start from 1 to infinity, it look like you start from a1, and then a2, and then a3, and so on. But if you start from n equal to 2 to infinity, it means you start from a2. I mean, the box here gonna be the same thing, but a2 they use the right hand as your height, but a1 they use the left hand as your height, left hand as your height. So basically, the stack that you have when you start from a2 is this one. The stack that you use when you start from n equal to 1 is this one. Which I mean, if you have the smooth function in the middle here, it's gonna be in the middle between them. So which means if you wanna check the, but I mean, you know that the series have the property that wherever you start, it's gonna be the same. If this one convergent, this one gonna be convergent. If this one divergent, this one gonna be divergent as well. So this is what we're gonna do for the integral test. In order to check the convergence of the series here, we're gonna integrate this thing. Because if we know that this thing is convergent, it means the series is convergent as well. If we know that the integrate here is divergent, it's gonna be divergent as well. So basically this is the theorem. So we're gonna use the integral test by construct fx, the same thing with an, just change n to x, and then you integrate from 1 to infinity. If you start from 2, you integrate 2 to infinity. You start from whatever the index, you start from that one to infinity, and you integrate this thing instead. And if it is convergent, you conclude that it is convergent. If it is divergent, you're gonna conclude that it is divergent. However, the function that you can use for the integral test must be the one that is a decreasing function. Otherwise, it's gonna be not okay to use the integral test because the function go up and down, up and down. No, it must be the decreasing function. So before using the integral test, we're gonna need to check that the function is decreasing. Okay, so this is the integral test. If f is continuous, positive, decreasing, then we're gonna compute integral from 1 to infinity fx dx, and the pattern of convergence gonna be the same for this integral and summation. So to sum up, if you want to use the integral test, what you have to do is the first one, check that the function is continuous, positive, and decreasing. Check. Once you check it, so you integrate this thing, step 2. Step 2, integrate that one. Step 1, check first if it is the condition is okay. Step 2, integrate. And then once you get the answer, step 3, once you get the answer from integration, if it is a number L, make a conclusion, convergent. If you get plus or minus infinity, say divergent. For the series, okay? Yeah, it's gonna be the same thing with the integral. Okay, it is not going to be easy until you see the example, but yeah, we're gonna see the example in a minute, but this is a theorem. So you need 3 steps. Check this first, and then compute that one, and then make a conclusion. Okay. So of course, example gonna help you to learn this thing. So this is called the integral test. Let's take a look at least one example today, and then we're gonna do 2 more next week. Okay. Let's do it, and then well, if we have time left, we're gonna just I will stay for questions for those of you who want to ask something about homework. All right, so example 12, let's apply the integral test for this one. Summation k start from 1 to infinity, k over k squared plus 1. Take a look, everyone. If you don't use the integral test, what you can do? You have to think this way first. If I take limit, the limit is 0, right? Because the bottom is heavy. So the divergence test cannot be applied. Because the limit equal to 0, you cannot conclude it from the divergence test. And also, this is not the geometric series. Because you don't see anything to decay at all. So this is not geometric series. It is its telescopic series. Did you see something minus something that you minus something that you can cancel out? I don't see anything minus sign here. You cannot cancel out anything. So telescopic is not okay. Once you feel like okay, divergence test is not okay, geometric is not okay, telescopic is not okay, integral test then. Okay, so let's try to do the integral test. Okay, before doing the integral test, we're gonna do step 1. Let's start by define fx equal to x over x squared plus 1. We need to check that this function is continuous, positive, and decreasing when x greater than 1. Okay, how do you, okay, it is obvious that f is continuous and positive. For continuous and positive, you don't have to check it because it is clear. You can see that when you plug in x greater than 1, this is positive, right? This is also positive, so it's always positive. And when it is continuous, it's always continuous because there is no hole here. Now, what you need to know is it decreasing, right? So you can check the decreasing by taking derivative. From count 1, you take the first derivative. If it is bigger than 0, the function is increasing. If it is less than 0, the function is decreasing. So we're gonna take the first derivative, and we hope that it's gonna give us negative number, so it is decreasing. Some of you already forgot how to do this. Low d high minus high d low over low square. Low d high minus high d low over low square. This is the quotient rule. And then that is x squared plus 1 minus 2x squared over x squared plus 1 squared. So basically, for sure, this term gonna be positive. And on the top part, it's gonna be 1 minus x squared, which is less than 0 now because x bigger than 1, everyone. X bigger than 1. When x is bigger than 1, x squared going to be bigger than 1 as well. So 1 minus something bigger than 1. The top term here going to be negative. So negative over positive, it's going to be negative, which means it favor our result. So we're going to say that my answer here is f is also decreasing. So now I already checked the condition 1. If you don't check it, if this is 10 point, if you don't check the condition, you get about 6 point. You lose like 4 point because you don't check the condition.
Even it's correct.
Yeah, I mean if it is correct, you still lose like about 40% because you don't check the condition. So make sure you say that it is continuous, positive and decreasing. But you know, on the exam, I probably say part A show this and this, you know, for 4 points. So you should be able to like know how that you don't forget how to do it. All right. So the second part, now we're gonna integrate fx dx. And if it is convergent, the series is convergent. If it is divergent, the series is divergent. So you're gonna integrate from where to where? Look. 1 to infinity, so you just do 1 to infinity. So let's do the improper integral that we just did here. So it's gonna be limit, right? Limit t go to infinity, 1 go to t, right? Because we just learned it on the first week that you can replace t by infinity and then take t to the infinity. Fx here gonna be x over x squared plus 1 dx. And then damn it, use substitution. So you're gonna okay, you can just make this correct. This is why I say integral test is hard, because you have to use so many things. So let's integrate this thing first so you can use it easily later. If you do use substitution, it's gonna be x over x squared plus 1 and then dx squared plus 1, right? So you get 2x. Hopefully everyone know what I just wrote over there, because you learn Cal 1 with me, you know my notation. And then yeah, x cancel, boop, boop. So you get 1/2, and then 1 over x squared plus 1 dx squared plus 1, you get log absolute x squared plus 1. Hopefully everyone remember this thing. This is what we spend a semester how to do the use substitution. At least everyone should be able to, oh okay, I feel familiar with this one. And then this is going to be limit t go to infinity. So if we integrate that one already, we get 1/2 log x squared plus 1. And then we're gonna plug in x equal to 1 to x equal to t. Okay. I mean, if you feel like you feel like this is way too hard for you, I would recommend you to save the integral test for the last one, because this is the hardest one for exam 1 for sure. And it's supposed to be the B plus or A level for the student who wanna get B plus or A. If you feel like you just wanna pass first, maybe you save this one for last, you know, because it's so long for integral test. You have to do so many things. And then now you integrate this one, you plug in t and 1, so you're gonna get 1/2 log t squared plus 1 minus log 1/2 log 2. And then when you plug in t here, so the answer should be infinity, right? Because this is constant. This is t squared plus 1 gonna go to something big. Log something big is infinity as well. So this go to infinity minus constant, so it's just infinity. Which means summation, integrate 1 to infinity, fx dx diverge. And by the integral test, the series k over k squared plus 1, k start from 1 to infinity, is divergent as well. Whatever you get here, divergent or convergent, you conclude the same thing, because it should match with the same thing. By the theory, it's going to be the same. So you have to well, if you know how to do improper integral, yeah, it's gonna be okay because the result gonna be the same. Sounds good? I think this is 1 hour already for you. Maybe we should like stop here and then I'll stay for questions. But if you wanna do it beyond this class, you can do B and C late and then check with me on the Monday, because when we come back next Monday, we're gonna start integral test question B, question C, and then we're gonna wrap up with the P series, and then we're gonna summarize everything you need to know for the exam one. Just get ready, everyone. The exam one gonna be on February 1st in class. Is it pretty soon? February 1st is like in 12 days. Okay, nah. So start homework today, and then next week we're gonna do more example on integral tests, and then maybe talk a little bit about homework, and then wrap up everything for exam one. Okay? Sounds good? Well, I'll stay for questions. If you have questions, let me know. So I'm gonna stop recording now. Thank you.